Bismillah ar-Rahman ar-Rahim. Welcome to the week 1 for basic engineering mechanics. I hope that all of my students are watching this video. So in this lecture we will be covering chapter number 1 of our textbook, and as I already told you in the previous lecture that this chapter is about the general principles that underline all of mechanics. So what I mean by that is so we would learn about the basic quantities, and we would learn about what is force, and there would be some idealizations that we would be using for the most part of this course, so we would learn about those. And then we would learn about the laws of motion. Laws of motion, you might have already learned them in your during your intermediate studies. So they form the basic of all mechanics, and we would study a bit of gravity, and then there will be some mathematical things that we need to know for the course. Okay, so let's start. You might have already learned that basic quantities are these measurable quantities like length, mass, time, temperature and electric current, and we call them basic quantities. That all the other quantities can be represented as products of these quantities. So for example, we have speed. Speed is also a quantity. It is a measurable. We can measure speed, but if we measure speed we can always represent. So let's see. So we have v equals the velocity equals distance over time. So we can always say that the dimensions of velocity are length over time. So to measure speed we can just use the units meters per second. So similarly we have quantities like force. What is force? Force is just mass times acceleration, and so mass has the units of kilograms and acceleration has the units of meters per second squared. So you understand where I'm getting with this, that any other quantity other than these 5 quantities we can represent them in terms of these base quantities. So that is why these are called the base quantities. Okay, so let's move on. So what are the Newton's laws of motion? So we have Newton, as most of you already know, is the world famous physicist who lived in the 16th century. Actually I should say 15th century, and he gave these 3 laws of motion which govern all of classical physics, I can say, and say they are very simple to understand, but again at the other time they were also very they changed a lot of physics. A lot of what we knew before Newton changed after Newton came. Okay, so what is the first law of Newton? That every body remains in state of rest or uniform motion unless acted upon by an external force. So this is the essence of Newtonian mechanics. So the first law is, first of all, we have what is called the state. A state can be a state of rest or of uniform motion, and unless there is an external force applied on any body, it would keep on its original state. So previously, before Newton came, people thought that bodies have two different states. Body has a state of rest, so there is a block lying on the surface, so, and another state where this block is moving with a velocity v. So Newton came along and said that these two are basically, this is also an inertial state and this is also an inertial state. So we can treat them both very similarly in a lot of ways. Okay, and unless there is a force acting on any body, it would keep on moving at a constant velocity. That velocity can either be zero, so this case we can say that velocity equals 0, and this case we can say that velocity not equal to 0. But in both of these cases, unless there is an external force, the body would keep on doing what it is doing for as much long time as there is. Okay, so this is the first law of Newton, and this is also called the law of inertia. So why would we call it law of inertia? So the idea here is that anything, this property of an object to try to stay in its state is called the inertia of that state. And so the first law of Newton also means that there are inertial frames. Any frame of reference which is moving with a constant speed would be called an inertial frame. So that's the law of inertia. The second law is probably the most popular, which is F equals ma, and it is, you might think that this does not mean anything, so we say that there is some quantity F which is equal to mass times acceleration. So why don't we just define another quantity? So let's say I can define another quantity u, which is equal to mass times acceleration squared. So let me just fix my A, was not the nicest A. Let me get the eraser. Okay, so we have mass times acceleration squared. Again, in terms of visual, I just defined a new quantity u, which is just mass times acceleration squared, and Newton just defined a quantity which was mass times acceleration. You might think that I just did something which similar to what Newton did, but you would be wrong, because force is a very, very useful quantity. So for example, we have force of gravity, and then we have another force, we have force of electrostatic. So the idea is there are many different forces so force of gravity, if a system has gravitational force, then the force of gravity would be equal to mass times acceleration, and if the force is electrostatic, again it would be mass times acceleration. So basically what second law is stating is that any external influence on a body is through a force, and that force produces an acceleration in the body. It does not produce a velocity, it does not produce a position, it produces acceleration. So in some sense the second law of Newton is very, very deep if we understand it truly. Okay, so the next is the third law of Newton, which basically says that action has equal and opposite reaction. What do I mean? That if, so we have two objects, so object A and object B, and so this object A, and they are tied with a knot. So this object A is pulling object B with the force of Fa, and Fb is pulling with this, and so this basically means that the force applied on A by B is equal to the force applied on B by A. So for example, if we have a person, so let's try to make a boat here. So if we have a boat, so that's my, and we have water here. So a person in the boat wants to jump off the boat. So to jump off the boat, the person would kick the boat like this. So person would be applying a force on the boat in towards the left, and then the boat would apply a force on the person to the right so that he can jump over to the side, and in the meantime the boat would also move to the left. So here we can see that action of the person. What is the action here? The force applied on the boat by the person is the action, and the force applied by the boat on the person is the reaction. So every force has equal and opposite reaction. So that's the third law of Newton. So let's move on. So the next thing we're going to learn is this is again the force can be a push or a pull, and force equals ma. This is the first law, second law of Newton, which basically means that if any effect of on a body by any external agent is through causing a change in acceleration. So, and what's the Newton law of gravity? Newton law of gravity basically means that two objects which have masses, they would attract each other through a force, and the force is given by G times m1 times m2 over r squared. So this is the same like sun and moon. So we have a sun. Let's make a better sun here. We have the sun, and then we have the earth revolving around the sun, and then we have the moon revolving around the earth. So the force between the sun and the earth is also force of gravity, and the force between the earth and the moon is also force of gravity. But for the most part of this course, when we would say force of gravity, we would basically mean something like this. So when we are near, so force of gravity when we are on the earth, whenever we are on the surface of the earth, let's see, and we are very, very close to the surface of the earth, we can basically show that the force of gravity is m times g, where g is the acceleration due to gravity, given here, and we usually refer to G. We take the value of G for this course to be 10 meters per second squared. The actual value you might already know that it is G is equal to 9.88 something meter per second squared. But for this course we would be taking this value of G. Okay, let's move on. Okay, I need to remove this. Okay, so as I discussed earlier, that there are some idealizations I will be using for the most part of this course. The first one is the idealization of a particle. So whenever we would talk about a particle in this course, we would mean that something which has a mass but it has no volume and it has no geometry. So what I really mean is that it's actually just a dot in the space. So let's see, even if I make the smallest dot, I can always zoom in on this dot and see that it would have some geometry and it would have some volume. But we here would assume that any particle has no volume and no geometry. So here we look at this example of a hook. So if we really zoom in, so if we look from far away, the hook would look something like this. Okay, so this is my hook and these are the three wires connected to 3 ropes connected to the hook. Okay, but if I were to zoom in, in this area, I would see that hook has a definite volume and it has a shape, it has a geometry. But for the purpose of our problem solving, we would just assume that this hook is just like a particle. So all of these forces are basically applied on the same point in space. Okay, so this is what I mean by a particle. And similar to this is the concept of concentrated force. Again here, although these 3 forces are not applied at the same point, this force of 200 pounds is applied at this point, and this force of 100 pounds is applied at this point, this force of 300 pounds is applied at this point. But for the purpose of this problem, we can assume that all of these 3 forces are applied at this point. Again, because this hook is so small that its geometry will not affect the overall picture of our problem. So that is why we are able to make this generalization. So we would be using these generalizations very, very often in this course. So you guys would get used to it, inshallah. Again, the next idealization we'll be using in this course is that of a rigid body. When I say rigid body, I mean that something which has a mass, which has a volume, but which has a fixed geometry. So the geometry of the system does not change. Again, this is also an idealization. If we look at any object, so let's see, if we have a box, anytime there is a force on a box, the shape of the box would change because of the force. Okay, so if we have tensional stress, so this means that there is somebody pulling the box from the sides, the box would shrink. If we have shear stress, the box would change shape like this. If we have compressional stress, that means somebody is pushing the box from both sides, then again the shape would change. But this would complicate our situation a lot. We won't be able to solve our problem very easily if we look at the change in geometry. So if we have something which is very strong, so let's assume that I have this glass here, okay. So if I push this glass, the shape of the glass does change. It changes very little, but it does change. So but if I assume that the shape of the glass does not change, I won't be making a very big error in the calculation. I would still be able to solve for all the forces, for all the unknowns, without making a lot of without making any big errors. So that is why we are able to use this generalization and idealization. Okay. So the next we want to talk about prefixes and significant figures. Again, because in this course we would be using many prefixes, and we need to be able to understand how to round off significant figures also. So let's talk about prefixes. So we use prefixes to represent very big numbers or very small numbers. So as a basic example, so we have something called a kilometer, which is basically just 1,000 meters. And anytime we just want to represent 1,000 meters, we would just say kilometers. Similarly, we have mega. Anytime we want to represent something which is of the order of 10 to the power 6, we just say mega. 10 to the power 9, giga. 10 to the power 12, tera. Similarly, if we are going to represent something which is very small, we have deci, centi, milli, micro, nano, pico. So for example, the radius of an atom is of the order of 10 to the power, it is 10 to the power of minus 10 meters. So we can also say that it is of the order of 0.1 nanometers. Okay. So this is just another way to represent this. Okay. So you have to be very careful when we use these prefixes and significant figures. Okay. And the second is rounding off. Okay. So when we say that we want to round off a number to 2 digits, so rounding off to 3 significant figures, so we just want to take these 3 significant figures. So if the last one is 4 or less than 4, we just remove it and just write 2.53. If the last number is if the fourth number is bigger than 5, we add 1 to the 3, so that we get 2.54. And if the last number is 5, then again we add 1 to 3. But this adding 1 is when the last number is odd, we would add 1. If the last number is even, we won't add 1. Okay, so this is the part where it gets a bit tricky, but you might have already learnt it during your FSC, the technique of rounding off numbers into significant figures.